When coastal waters force their way into urban streets, the sheer volume of water easily overwhelms the built environment. Take Red Hook, Brooklyn. Built on low-lying coastal landfill, its geography makes it highly vulnerable to inundation from the surrounding harbor. To protect the neighborhood, engineers proposed the Red Hook Coastal Resiliency Project, or RHCRP. The system is designed to provide a continuous barrier against a 10-year coastal surge. This map shows the modeled terrain elevation of Red Hook with the proposed RHCRP alignment overlaid in pink. You can see exactly where deployable barriers and static walls would cut across the neighborhood's topography. But modern coastal infrastructure faces two opposing hydrological threat factors: ocean-driven storm surge pushing water inland, and short-duration, high-intensity rainfall dropping water directly from above. This graph illustrates the historic data profile from 2012 Superstorm Sandy. The orange line indicates the tide level spiking to 11.3 feet, driven almost entirely by storm surge, while the blue bars show negligible precipitation. Contrast that with Tropical Storm Ida in 2021. Here, the graph shows a massive precipitation spike, hitting 3.5 inches per hour, while the tide level remains relatively low. This creates a strict engineering paradox. The rigid walls required to block incoming ocean water inherently alter the natural drainage pathways of the protected inland areas. In dense urban environments, covered in impervious concrete and relying on aging underground drainage, any topographical alteration has immediate consequences. By running two-dimensional hydrological and hydraulic models, we can observe the outcome. Rigid coastal barriers act as reverse dams, trapping extreme precipitation and shifting the flood risk to the dry side. Let's isolate the precipitation variable using the Tropical Storm Ida profile, where flooding is driven almost entirely by extreme peak rainfall. This map shows Red Hook's existing conditions during that event. Without any coastal barriers in place, we see minor pooling, primarily contained along Dwight Street. Now, we seal off the coastline by fully deploying the RHCRP barriers and run the exact same rainfall event. This is the model output for the RHCRP conditions. The barrier blocks the natural overland flow of stormwater, preventing it from draining into the harbor. Flood depths on the dry side increase by up to 2.0 feet compared to the baseline conditions. Simultaneously, the unprotected wet side of the wall experiences negligible inundation during this rain-heavy low-tide event. If we leave the deployable barriers open during the storm to allow runoff to escape, the model yields this map. Even with gates open, permanent regrading and static walls still obstruct surface flow, increasing dry-side flood depths by a full foot over existing conditions. Optimizing infrastructure exclusively to seal the coast creates a severe immediate vulnerability to flash stormwater runoff for the very community it surrounds. We can observe the opposite failure by shifting our analysis to the storm surge variable, utilizing the Superstorm Sandy data profile. This map illustrates the historical baseline inundation footprint of Sandy. The water disperses unhindered across the terrain. Engineers refer to this physical space as the flow area, the room available for incoming surge volumes to spread out and naturally dissipate their energy. This map shows the proposed RHCRP barrier alignment, which is routed tightly against existing waterfront structures, drastically reducing that available flow area. As a result, incoming storm surge becomes trapped within the topographic pockets formed by the new walls and the old buildings. The localized depths on the wet side are forced up to 8.0 feet. That is approximately 3 feet higher than the inundation experienced in those exact areas under existing pre-wall conditions. While the barrier successfully shields the dry side from this specific surge, it artificially amplifies hydraulic pressure and destruction on the unprotected wet side. To understand the limits of this system, we run the ultimate stress test, the projected 2080s 10-year design storm. This graph establishes the primary variables. Driven by sea level rise, the peak tide hits 9.5 feet, confronting a barrier built to a 10-foot protection height. When a rigid barrier intersects with dense urban geometry, it creates a hydrodynamic bottleneck known as the canyon effect. Because the surge cannot naturally disperse, the constriction forces the water elevation to rise artificially high at the bottleneck. This setup forces the water level to surpass the 10-foot protection height, overtopping the barrier. Once the water overtops, the barrier acts as a dam, trapping the volume on the dry side. Unlike natural flooding, this hydraulically trapped water cannot recede or circulate back into the harbor as the ambient tide falls. This map highlights the resulting data, showing massive pooling of trapped surge water permanently isolated in low-lying inland areas. When hydrodynamic forces are constricted by topography, the protective wall itself becomes the mechanism of entrapment. Under current, baseline climate conditions, this map demonstrates the system functioning exactly as intended, keeping the inland area completely dry. Compare that to the 2080s failure map. Sea level rise and overtopping generate a stark increase in inland flooding. These models rely on a critical assumption. The underground drainage systems are operating at or near maximum capacity from the onset of a storm. Because those subsurface systems are overwhelmed, surface grading and physical barriers dictate 100% of the water's movement. The RHCRP successfully trades open coastal circulation for walled protection, but at a severe cost. Under extreme precipitation or future sea level rise, this walled protection guarantees higher peak flood depths on both the wet and dry sides than if no barrier existed at all. True coastal resilience cannot be achieved merely by building a wall to block the ocean. It must actively account for and manage the topographic isolation it imposes on the community within.